All right. So, hello, everybody. So, we have the pleasure today of having Valentino Tosatti, who will tell us about the Kähler-Ricci flow and MMP. Please go ahead.
Okay. Thank you very much for the kind invitation, and thank you all for coming. Please feel free to interrupt at any time with questions. This will be a pretty overview talk. Yes. So let me just start with some basic setup. So as you probably know, I'm more of a geometric analyst, a complex geometer. So I'll try to make this algebraic geometry friendly, but there will still be some analytic terminology at least. So in the talk, X will be usually a compact Kähler manifold. So of course, feel free to think that X is projective. I will assume smoothness, so manifold. A lot of things would go through, let's say, for KLT singularities, and I will elaborate on that. However, many of the actual analytic things that I will discuss really need a smoothness. So in any case, I will elaborate later on less smoothness. So you can pretend that these are allowed to be KLT for now. And then the H11 will be one of the protagonists, the cohomology group of closed real 1-1 forms. So think of this as a transcendental analog of the space of R divisors, say, which is up to numerical equivalence. And in this H11, there's the distinguished cone. I would denote it by CX instead of KX, because KX is usually the canonical bundle. So CX is the cone of cohomology classes of Kähler forms. So omega will denote a Kähler form. I will usually call it a Kähler metric. So it's a closed real 1-1 form. And the coefficients are positive definite. And these cohomology classes, the parameterized Kähler metrics, define an open and convex cone, here pictured from a famous picture stolen by Jean-Pierre Desmailly's slides. And the closure are going to be called the NEF classes. If we are talking about line bundles, for example, a line bundle has a first-chain class, C1 of L, and the first-chain class lives in this H11. And the line bundles whose first-chain class is scalar are exactly ample. The line bundles whose first-chain class is NEF are NEF. This is, sorry, if the manifold is projective. So these are transcendental generalizations of the notion of ample and NEFness. If I have a Kähler metric, the other thing, main character we will need is the Ricci curvature, which is also a closed real 1-1 form, a Ricci of omega. Locally, it's the dd bar log of the determinant of the metric up to this minus I over 2 pi. And this is just the curvature of a smooth metric on the anti-canonical bundle. So the cohomology class of the Ricci form is the same as minus kx. Okay, so independent of the metric, of course. Now the Ricci flow is going to be the, I guess, famous evolution equation of Kähler metrics. So omega 0 will usually be the initial metric of the flow, and a family of Kähler metrics omega t with, in general, different cohomology class will be called the solution of the Kähler-Ricci flow if, okay, they depend smoothly in this time parameter t, which lives in some interval 0 open to big T, sorry, 0 close to big T open, and the time derivative is minus the Ricci curvature, and the initial value is the omega 0. So this equation makes sense, at least formally, because both sides are closed real 1-1 forms. And a fundamental result of Richard Hamilton in the 80s is that you can always solve for some short time. This is true even in the Riemannian world. You don't even need Kähler. And the solution is unique, and it has a maximal time interval, big T. However, in the Kähler world, there is a formula for this big T, because we can just look in cohomology in this H11, the time derivative of the cohomology class, taking the Ricci flow equation and passing to cohomology, is minus the cohomology class of Ricci, which doesn't depend on time. This is C1 of Kx. And so you can immediately deduce that as long as the flow exists, the evolving cohomology class moves in this segment, the initial one plus T times Kx. And so in particular, as long as the flow exists, for time T, this class has to be in the Kähler cone because there is a Kähler form in this class, the solution of the flow. And the really nice theorem is that the converse is also true. So this was proved in full generality by Tian and Zhou Zhang in '06. That's a formula for the maximal existence time. The big T is exactly as long as this segment stays inside the Kähler cone. And this supremum, of course, can be plus infinity. And if you replace here a Kähler cone by Neff, taking closure, it's exactly the same. So you could say as a Neff threshold of this segment. So here is the picture, I guess, of the initial class moving along a segment, and in this picture here, it hits a wall in finite time. So you can easily see from this equation that when does that picture not happen? So when do you exist for all the positive time? That's exactly the same as when Kx is an F in this analytic sense. So the first Chern class of the canonical bundle is in the closure of the Kähler cone. So and of course, if the manifold was projective, this notion is, as I said, is compatible with the usual one, the intersection with curves. So minimal model, you could say, smooth. So this, I believe it was this picture here, at least the picture in cohomology, which inspired Paolo here, Cascini and Gabriele La Nave, and independently Song and Tian around '06 again. They propose a direct relationship between the minimal model program, now we would say with scaling, and the behavior of the Kähler-Ricci flow. The proposal, of course, was when X is projective, and let's say the initial class is an ample line bundle, C1 of H, and then you can see this would be H plus TKX, and the first singularity exactly looks like the first time when you need to do some surgery along the MMP with scaling. So that was the initial proposal had several components, and I want to somehow illustrate them by studying the behavior of the flow. So as I will explain near the end, so far, most of the results and basically all the relationship between MMP and Kähler-Ricci flow has gone in a one way. So from the MMP to the Kähler-Ricci flow, that's basically the content of the talk. And I will try to advocate the hope to find something going backwards from Kähler-Ricci flow to MMP. And I don't think there are any results yet in that direction. So from the point of view of the Kähler-Ricci flow, you can say that the ultimate goal will be to understand the behavior of the evolving matrix as you approach this maximal time big T in general. So for arbitrary X and arbitrary omega 0. So this ultimate goal, I can say, could also make sense in the much more general setting of a Riemannian manifold, let's say closed compact Riemannian manifolds and Riemannian matrix and Riemannian Ricci flow. And as such, this ultimate goal is completely hopeless in that category. It's really completely hopeless. However, in the Kähler category and the Kähler-Ricci flow, I want to argue that this goal is maybe not exactly within reach, but we know a lot about it. And thanks to the MMP, there is a complete conjectural picture of this. So, okay, that's basically what I want to discuss. So one should start from the easiest case, which is when C is a curve, so complex dimension 1. This was solved by Richard Hamilton and Ben Chow in the late 80s, early 90s. So there are three possibilities according to the positivity or negativity of the canonical bundle. So here I put in an arbitrary order. So one case is when the canonical is trivial. So the curve is C is an elliptic curve. Then the maximal existence time, of course, is infinity. The canonical bundle is trivial, therefore Neff. And the flow converges smoothly to a Ricci flat. In fact, I should say flat metric on the torus. So the torus has many flat metrics coming from the complex plane. Those are like constant metrics on C. And the flow will converge to one with the same cohomology class as the initial one. And the second case is when the canonical is ample. So these are Riemann surfaces of genus 2 or higher, then again, ample implies nef, so the maximum resistance time is infinity again, and the metric omega t, you can check that the area is growing with time if you compute the total area. So it's convenient to rescale by t. Here, of course, t will be positive. I want to look at t large. And then if you rescale by t, now the volume is comparable to constant. And you can now expect to have reasonable convergence. And in fact, you do have smooth convergence to a negative Kähler-Einstein metric. So here it means, in fact, hyperbolic metric with constant negative curvature, -1, say. So these two cases clearly give you an analytic approach to uniformization of regular surfaces. And the last case, when minus kc is ample, so C is P1, is actually the hardest by far. And here, finally, of course, the existence time is finite. So you have a singularity. And it's easy to check in homology that the total volume shrinks to 0 in that finite time. So the sphere somehow infinite time disappears, but you can rescale by big T minus little t. So if you rescale now, the volume does not shrink anymore, and this converges smoothly to a Kähler-Einstein metric with positive Ricci curvature. So again, here this is the same as being a constant curvature metric on the sphere. And these are the Fubini's 2D metric up to isometry. So it's one of the Fubini's 2D. So this would be the schematic picture of what happens on the sphere. So this last theorem is particularly hard. So this is where Ben Chao entered. So at the end of the day, one can recover the uniformization theorem via Ricci flow. Even though the original proofs were using the uniformization theorem, there were later additions where you can actually give an independent proof. So the next case one should look at is dimension 2. So S will be a compact Kähler surface, doesn't have to be projective. So again, the discussion splits into the case of finite time or infinite time. So first, let's look at the finite time. So when the canonical bundle is not nef, so the flow stops at finite time big T. And now there is a new situation which you didn't see in the curve case, which is that you can have the volume not go to 0 in finite time. So this can happen. And this means that if I look at the limiting homology class, which is the initial plus big T Ks, this limiting class is nef and big and not Kähler. So this can actually happen. And then it's not hard to see that in this case, the surface contains finally many disjoint -1 curves that you can blow down. So it's the blow up of another smooth surface S prime. And the limiting class is a pullback of a Kähler class from S prime. And then, so your nef and big class, you somehow contract in this case, it would be the null locus, and you make it into a Kähler class on a new space. And then Song and Weinkoff, this is much more recent, in 2010, they proved that away from the exceptional locus of this contraction, you have smooth convergence to some metric which is pulled back from S prime. This metric omega t, in fact, in general, is singular at those points in S prime where you are blowing up. However, even though it's singular at these points, you can still restart the flow by some regularization procedure. And the flow continues on S prime, and the whole process they prove is continuous in the Gromov-Hausdorff topology. So that's when you only look at manifolds with metrics as metric spaces. So you ignore all the complex structure and everything, just view them as metric spaces. So, all right. And the other option, if you have a finite time singularity, is that the volume does go to 0. So the limiting class is not big. And now there's again a dichotomy. So this limiting class could be the 0 class or a non-trivial class. So in the non-trivial case, then one can easily prove that the surface is ruled. So it's a P1 bundle over a curve. And again, the limiting class is the pullback of a Kähler class from the base curve. And we expect that the flow should smoothly collapse these P1 fibers in finite time and converge to the pullback of a metric on the Riemann surface. And it's almost embarrassing to say that this is unknown in general, even for P1 times P1. So the simplest possible P1 bundle you could think of. In general, we do not know this smooth convergence. So we know there are partial results known, so you have convergence in some weaker sense, but in general, this is a very hard problem. So again, mimics what happened earlier in the case of P1. In any case, that's certainly expected. And on the other hand, when the limiting class is the zero class completely, that means that certainly minus KS was ample because it's a Kähler class. And so the surface has to be Fano. And also you can do the same rescaling as you did for P1. And this one converges smoothly to Kähler-Ricci soliton, which is a generalization of the Einstein equation where the Ricci is equal to 1 plus the Lie derivative of the metric with respect to a holomorphic vector field. So this is a solution of the Ricci flow. I mean, the limit is a solution of the Ricci. You can think of it as a solution of the Ricci flow, which would move only by holomorphisms, pulling back the metric by holomorphism and shrinking. So this is due to the work of many, many people that I did not list. But first, there is the theorems to prove that all Fano surfaces admit such Kähler-Ricci solitons. This goes back to, I don't know, Siu, Tian, so in the 90s. And then the fact that the flow actually converges to a soliton, I mean, I will mention it later. In full generality, it was proved by basically Bamler and Chen and Wang. So this was known as the Hamilton-Tian conjecture, but I will mention it later because it's in higher dimensions. So just slide is just to indicate that finite time singularities could be quite challenging to understand, especially in the case when it's a volume collapsing. And I mean, if you want, I can say now that you can already see the two steps of the MMP. The first bullet point here is just a divisorial contraction, and the second bullet point is a Fano fibration, or you want to say Mori fiber space, but that's not guaranteed to be the case here because I picked an arbitrary initial class, so the class on the boundary may correspond not quite to an extremal ray in the dual cone of curves, but to an extremal face. But in any case, if you choose the initial class omega 0 generically, this would be Mori fiber space, the part 2. I see. I mean, I guess. Suppose yes.
Can I ask a question about the non-collapsing case?
Yeah, sure. Yes.
So when you say that the process continues in the Gromov-Hausdorff topology, are you saying S prime is a Gromov-Hausdorff limit under?
Yeah. So if you take S and omega t, and then you take the limit when t goes to big T from the left. On the other hand, you can take S prime and omega, I don't know how to call the new time parameter, S. That's the one on the new surface S prime. And then you take the Gromov-Hausdorff limit when S goes backwards to the time. And those two Gromov-Hausdorff limits are the same metric space, isometric. Yeah. So and they are isometric if you want to the metric completion of what I call omega big T. So omega big T lives on S minus those -1 curves. You can also think of it living on S prime minus points. And when you take the metric completion of that, that's the time slice. At the critical time slice, you have this singular metric space. So yeah, basically you have this family of metric spaces dependent on T. They're all smooth manifolds except at the time big T, where you have this singular one. But yes, the topology of the manifold is changing.
Okay.
So yeah, it's kind of interesting. Yeah. So in particular, maybe I can remark that there is no need to do any surgery by hand, like in Perelman. The surgery here is somehow done automatically by the flow. All right. So on the other hand, we can also consider the remaining case when the time is infinity, so no finite time singularity, namely the case when S is a smooth minimal surface, Ks is an F, minimal in the usual sense, not in the classical sense. So then the Kodara dimension is not negative, I guess, by abundance or non-vanishing. And you have 3 cases. So when the Kodaira dimension is 2, that's a minimal surface of general type. In this case, the flow, again, the volume expands. If you just check in cohomology, the volume is growing. So we need to rescale by t. And if you rescale by t, this converges again smoothly away from the augmented base locus of the canonical bundle, which is some configuration of -2 curves, where the canonical bundle dots trivially, intersect trivially with them. And the limit is, again, a negative Kähler-Einstein metric with potentially singularities. And in fact, it turns out to be the pullback of an orbifold Kähler-Einstein metric on the canonical model SCAN, which indeed only has orbifold singularities. So you have, again, some kind of uniformization theorem for minimal surface general type. The limit is Einstein, negative Einstein. So since we are not on curves anymore, these are not hyperbolic metrics necessarily, but they are as good as you can hope for. And maybe I jump to the last one. The last one, sorry, this was done by Tian and Zhang. There was some earlier work by Tsuji. I didn't put it in the 80s, and it was completed by Tian and Zhang. And maybe also ACDU gets the area here, although I'll mention it later in higher dimensions. And in Kodaira dimension 0, then the canonical bundle is actually torsion, and the metrics without any normalization converge smoothly to a Ricci flat Kähler metric. This is what I would call the Calabi-Yau case, or Calabi-Yau in the loose sense. And this was approved by Cao in the 80s. And finally, the hardest case is the case of intermediate Kodaira dimension 1. So the surface is known to have a structure of an elliptic fibration. So it's a minimal properly elliptic surface. And it's again convenient to rescale by t. So omega t, the volume is still growing. If we rescale by t, unfortunately, the volume now collapses. But the cohomology class converges to kx, right? The cohomology class of omega t was omega 0 plus tkx. If you divide by t, it converges to kx. And what is known here is that away from the singular fibers of this fibration, you have smooth convergence to the pullback of a metric from the base, which is, again, an Einstein metric with a twist. So it's a negative Einstein metric. Ricci is minus itself, plus a Weil-Peterson form, which is semi-positive and measures the variation of complex structure of the elliptic curves, the fibers. And this twisted Kähler-Einstein lives on the base, minus finally many points, the image of the singular fibers. And so this was proved by Song and Tian with a weak convergence, and the smooth convergence was improved by work of myself, Mark Gross, and Yuguang Zhang, and later Feng and Zhou Zhang. There will be 3 Zhangs in this talk, so I apologize for the confusion. Okay, so this is you can say that the easy cases, in fact, some of them are really quite hard, the classical cases. And I want to discuss the situation in arbitrary dimensions and also in more detail how one can use MMP related results to help understand the flow. So first, again, I want to discuss the case of finite time singularities and later the case of infinite time solutions. So the setting now will be in arbitrary dimension and not necessarily projective. So compact Kähler manifold and omega t would always be the solution of the Kähler-Ricci flow without any strange normalization. DGDT is minus Ricci. And we assume we have a finite time singularity. So that's equivalent to saying that, oh, sorry, I forgot to change kx is not an f. So let's assume first kx is not an f. Then we have a limiting class. So I will conveniently call it alpha. This is the cohomology class that the flow limits to. So if you go back many, many slides, it's the class that you hit here on the boundary in finite time. And oops. And this class is certainly in F because an F cone is closed. And there was a conjecture about how could the singularities be forming along the flow. So the people studying the geometric flows, they're especially interested in where a curvature blows up or where curvature is bounded. Riemann curvature because of, again, earlier results of Hamilton that on the regions where Riemann curvature is not blowing up, the flow can be continued. So it can be continued as long as the Riemann curvature does not blow up. So the fact that there is a blow up in finite time is witnessed by the curvature exploding to plus or minus infinity. And so here is again schematic picture of a dumbbell forming a pinch, which is a total lie, but you can imagine this would be some higher dimensional version of this picture would be a more appropriate picture. And the singularity formation set, sigma, was defined by other people as these points where the curvature is not blowing up. So locally bounded near the point as you approach the singularity. And Feldman, Illman, and Knopf, they had conjectured that this is a subvariety, so a closed analytic subvariety. And if X was projective, then this would be an algebraic subvariety. So Zariski closed. And again, quite a while ago, I proved with Collins that this is true. In fact, the singularity formation set is the same as the null locus of this limiting class, namely the union of all positive dimensional, irreducible, analytic, closed subvarieties V, which intersect trivially with alpha. So the integral over V of alpha dimension V is 0. And equivalently, this condition of intersecting trivially with alpha just means that their volume along the flow is shrinking to 0 in finite time. So in finite time, the volume of the subvarieties goes to 0. You collect them all together, and this big union is Zariski closed. And away from this big union, if sigma is not all of X, then on the complement, you have a smooth convergence to a limiting Kähler metric. And by the way, sigma will be all of X if and only if the limiting class is not big, namely V equals X is allowed in this union. So, so that's the very first basic result somehow, the very basic step. This says that if you have a finite time, in particular, non-collapsing singularity, when alpha, the limiting class, is big, then there is this small subvariety sigma where bad things are happening, and away from it, the flow is converging perfectly nicely. And one expects now the sigma can be contracted complex analytically. And this is exactly a transcendental version of the base point free theorem, because if you go back, if you remember what alpha is omega 0 plus tkx. So imagine that omega 0 was an ample line bundle H. Then by Kawamata's rationality theorem, this big T is actually a rational number. And then that means that this class alpha up to clearing denominators, and if you subtract kx or some multiple of kx, this class is ample. So then Kawamata's base point free theorem exactly applies and would tell you that alpha is a semi-ample class. So, I mean, this line bundle alpha, the line bundle corresponding to alpha after clearing denominators is semi-ample. And that would provide you a contraction for which that line bundle is the pullback of an ample one. So the conjecture, which I formulated explicitly with Simeon Philip a few years ago, is that you should have the same thing for classes and Kähler manifolds. So for a compact, and in fact, I think Öring later extended it to the case of KLT singularities. So if you have a manifold and alpha 1-1 class, which is Neff, and again, those multiples are not important, so just say alpha minus kx is Neff and big, then there should be a contraction, meaning a subjective holomorphic map with connected fibers onto a, let's say, normal compact Kähler analytic space, Y, and alpha is the pullback of a Kähler class on this analytic space. Again, you can pretend that Y is smooth if you are unhappy with Kähler classes on analytic spaces, but it can be defined. And in fact, for the case of the flow, Neff and big, you can strengthen it to assuming that it's Kähler, because in the case of classes alpha for the Kähler-Ricci flow, this would be Kähler, this difference. So you can, if you want, you can just look at the case of the Kähler of this conjecture, and the conjecture is known now up to dimension 3 in this generality. So dimension 2 It's supposed to be easy, but I'm not assuming any projectivity, right? So there's a little work to do. I did it in the original paper with Simeon. Dimension 3, when it's scalar, was done by myself and Yuguang Zhang in the non-big case, and by Andreas Oehring in the big case. And finally, Das and Christopher Hakon, they did the general case of threefolds, including the KLT case. And in higher dimensions, if the manifold is projective, the same authors more recently covered that case also. So I think Christopher has an approach to prove this in general, and maybe he even spoke about this, right, in the previous talk here. So I will defer to him if you have questions about this. But certainly it sounds like there's a lot of progress on this conjecture, and it hopefully will be settled soon. So this would provide us with the desired contraction of the sigma. So the sigma here would be exactly the exceptional set, exceptional locus of F. And this would give us at least a new space where, okay, not quite, you would hope to continue the flow. Of course, in general, may not be exactly continuable on Y, but at least on a bimeromorphic model. So yeah, sorry, this is roughly what I was just saying. I just repeated the conjecture, and I was saying that this would be applicable to these finite time singularities, and you would only need the case of Kähler here. And then again, you have two cases. So assuming that you have this, you obtain this contraction F, and the two cases are the same as before. If the limiting class is not big, then this F would be a Fano vibration here, meaning that minus Kx is relatively ample, because as I said, you have Kähler here. And this is the analog of the P1 bundle from before, right? And what is expected here is that the flow should collapse these Fano fibers in finite time and converge to the pullback of a Kähler metric from the base of this Fano vibration in a suitable sense, away from the singular fibers. And even more, if you rescale, if you do the same rescaling as before, but you restrict to one of the smooth fibers, you should have, again, suitable convergence to a Kähler-Ricci soliton. So the fibers are all Fano, and you should converge to a soliton here weakly in a suitable sense. There are many technicalities due to the fact that not all Fano manifolds admit a Kähler-Ricci soliton. So, but let's ignore them. The convergence here, the issues in the convergence, so it's not in a smooth sense everywhere. And this is a major difficult problem, and it's only known when the base is a point. So when you have a Fano manifold map into a point, then this is proved. So the collapsing is proved by Perelman in fact unpublished work that was later written up by Natasha Sessum and Tian. And then the convergence to a soliton was the famous Hamilton-Tian conjecture proved by Bamler and Chen and Wang. And many people did intermediate work on this. And however, if Y is not a point, again, we have extremely partial results are known. So as I said, even the case of P1 times P1 is not done. So this is one major point where the behavior of the flow is very mysterious. And this next case is better when the class alpha limiting class is big. So you have a finite time singularity, but the volume is not shrinking to zero. You can call it a volume non-collapse singularity. Then if you have this transcendental base point free, you have this contraction, which is bimeromorphic. And it could be a divisorial or a flipping contraction. And if flips exist, well, I guess maybe they do in the Kähler setting. Christopher would know for sure. Then you expect that the flow can be restarted on the new flipped variety. And the process, again, should be continuous in the Gromov houses of topology in the same sense that Yue Qiao was asking earlier. So here, notice that after the flipping or the divisorial contraction, you may not be smooth anymore. You acquire singularities. So really, to make sense of this, you have to define the flow for, let's say, varieties with KLT singularities. This can be done in the weak sense, using the fact that the flow is a Monge-Ampere equation, and there's a theory of weak solutions of Monge-Ampere equations. But the actual analytic regularity of these weak solutions near the singular locus of these KLT varieties is extremely delicate. And again, there are only very partial results. So that's why most of the results I will mention today assume smoothness. So Song and Tian, in the projective case, they went through this, assuming the MMP, basically. and assuming termination also. And indeed, they proved that you can continue the flow in a rather weak sense through all of these finitely many divisorial or flipping contractions. So this case here, at least in a rather weak topology, can be understood. In fact, if the Kähler case is also done, I mean, say existence of flips, then presumably the results can be extended without too much pain to the Kähler case, I would imagine, because they're quite analytic in nature, the Song-Tian paper. So, okay, there are a few more points I would like to make about this finite time singularities. So, one is a conjecture. I'm not quite sure who to attribute it to. Is somehow folklore that when you reach any finite time singularity, of course, on a compact Kähler manifold, the diameter should not blow up to plus infinity. So the diameter is the largest possible distance between any 2 points, measured with respect to omega t. And then when t approaches singularity, you don't want points to escape further and further away. So this is definitely expected. And it was very recently, okay, maybe 1 or 2 years ago, proved in a very nice paper by Guo, Fang, Song, and Sturm, actually several papers, when the limiting class is big. So for the volume non-collapse case, this is now a theorem. Annoyingly, their proof does not work in the volume collapse case. So we don't know this for those Fano fibrations. This is unknown. And you can ask, how about the diameter lower bound? So, okay, the diameter doesn't go to infinity, but could it shrink to 0 in finite time? And certainly it can. Just the case of P1 shows you that. Or a Fano manifold, if you run the flow in a Fano manifold starting in minus kx, or in a positive multiple of minus kx, then the unnormalized flow indeed shrinks, diameter shrinks to 0 in finite time by a theorem of Perelman. So for Fano manifolds, you do have this finite time extinction. By the way, this extinction means exactly that the diameter goes to 0. It's equivalent to saying that the Gromov-Hausdorff limit is a point. So the whole manifold disappears to a point. And Tian had conjectured a while back that if you have a finite time singularity, then this extinction happens. So the diameter goes to 0, if and only if you are on a Fano manifold and you are proportional to the anti-canonical class. So basically a complement to the other conjecture. So, and there were partial results by Zhang Song and myself and Yuguang Zhang. And finally, just I think 2 months ago, my postdoc Junshan Zhang proved this conjecture in general, and he used heavily the Kähler MMP. In particular, results of Das and Haken were used a lot. So this is another point where the Kähler MMP helped to prove a conjecture about the behavior of the flow. So what is still I guess it was implicit in the previous discussion. Also, it was here. It is still unknown. Another that you have this one here, that you have a finite time collapsing if and only if you have a Fano fibration. So this would be settled if you can prove this transcendental base point free. So finite time volume collapse should happen if and only if you have a Fano fibration, and finite time extinction if and only if you're Fano in the right class. So for now, this is basically all I have to say about finite time singularities. As you can see, they're supposed to precisely go through the same steps of MMP with scaling, I suppose, because you're moving in the h plus tkx. And if we have these steps of the MMP, in particular transcendental versions, then we can hope to understand the behavior of the flow when you hit the singularities. And the non-collapsing case is always easier, and the collapsing case is always extremely complicated. So the last big topic is the case of immortal solutions, meaning when you never encounter singularities in finite time. So this is anyway what's expected to happen in general, right? So namely, start the Kähler-Ricci flow on an arbitrary x with arbitrary omega 0. Well, you may encounter some finite time singularity. It could be volume collapsed or non-collapsed. And if it's volume non-collapsed, you expect to have this contraction and a flip perhaps and continue the flow. If it's volume collapsed, you have this Fano vibration, expect, and you can continue the flow on the base of the vibration unless the base is a point, right? The extinction, which happens if and only if you are Fano and in the right class. So basically, if you believe all these previous slides, all the expectations, starting from an arbitrary initial metric on an arbitrary manifold and going through finally many of these surgeries, either you end up with a point and you stop, or else you end up on a new manifold or variety, which may be lower dimensional if you had encountered a Fano vibration. And on this final manifold, the flow should exist for all time. So again, implicitly, we're using termination here, that you expect that there are only finitely many of these singularities. After that, you have supposed to reach the case when the canonical bundle is Neff. And of course, it should also be KLT, but I will assume, as usual, that is smooth. So I will have now a compar Kähler manifold, and assuming that the canonical bundle is Neff. So, oops, sorry. This is the same as the flow exists for all time, positive time, or immortal. And naturally, there is the abundance conjecture here, or the Kähler version of abundance, which says that Kx should be actually semi-ample. But let's not assume it yet. So if we don't assume abundance, we still have some results. Again, the same paper of Guo, Fong, Song-Storm proved that if you normalize, again, this normalization is very, very natural, GT over T, because it makes you converge to the canonical class Kx. So if you normalize this way, again, the diameter does not blow up to plus infinity. And you can take Gromov-Hausdorff limits, but only sequential ones. So take any sequence, Ti going to infinity, you can extract some subsequence and the limit in the Gromov-Hausdorff sense, which is a compact metric space ZD, but it a priori depends on the sequence. And certainly we expect that this Gromov-Hausdorff limit is independent of the sequence, and it should be homeomorphic to a projective variety. It should be simply the canonical model of X. So this so far seems out of reach if you don't assume abundance, but at least without assuming abundance, you have some space Z with a distance D. However, so right now we don't know that it's canonical. You see, that it could depend on the sequences, and it has no algebraic or analytic structure as of right now. So it's not particularly useful yet, but it's supposed to be the base of the Ithaka vibration. So this is what we know without abundance. And again, I wrote down this conjecture explicitly 2 years ago about trying to understand the weak limit as currents. So again, assuming that you have an immortal solution, so the canonical bundle is Neff, and omega t solves the flow, and divide by t. Now, these are Kähler metrics on a fixed manifold, and the cohomology class is converging to Kx. So by abstract nonsense, weak compactness of currents, you can always take subsequential limits in the weak topology as currents. These are the dual of smooth forms. And the limit, I conjecture that you don't need subsequences, so you always can take a weak limit to a closed positive current, let's call it eta, which is in the first rank class of the canonical bundle, which has minimal singularities. This is a technical term of a Demai. And also, this limit should be independent of the initial metric omega 0. So wherever you start, you always get the same limit. So this eta would be the curvature of a semi-positively curved singular metric on Kx. I call it a canonical metric. Sorry, it's kind of a pun. A canonical metric on the canonical bundle. It's canonical because it would depend only on the complex structure of X. So it would be a God-given singular Hermitian metric on Kx with no negative curvature, which comes as, canonical limit of any of these flows. So I believe this object should be important, but the conjecture says that there is a unique such object. So as I said, you can always take subsequential limits and obtain several different etas, but they should all be the same. And this eta should have very good properties. In particular, it would be kind of regular in the sense that it should have zero long numbers. In fact, it should have bounded local potentials. It should be smooth on a Zariski open set. And I mean, being more and more optimistic, once you know that it's smooth, you can define the kernel, because it will be a differential form, semi-positive definite, and the kernel should give you a foliation. So it's pretty clear that on each open set where the rank of this eta is constant, it gives you an integrable distribution. So a smooth foliation, but it's not clear at all that it gives you a holomorphic foliation. But that's expected. And even better, the leaves of this foliation should close up, close leaves, and you should get the Ithaka vibration. Of course, this is just wishful thinking, but this is exactly what happens when the canonical bundle is semi-ample, as I will explain in the next few slides. So I'm not claiming that this can be done, but I'm saying that at least knowing that this eta exists, and at least proving some of these regularities, for example, that it has zero round numbers, if one could prove this a priori, it would be helpful. And this eta could be, being the curvature of a singular metric on Kx, one could try to use L2 theory, d bar on Kx with this metric to try to prove something, you know, generate some sections. But I mean, this is all far-fetched, and nothing has been realized of this, except if you assume abundance. So namely, you assume that Kx is semi-ample. So again, it doesn't have to be projective, so just a compare Kähler manifold with semi-ample Kx. So like a good minimal model. Then I want to know what happens to the flow. And again, the discussion splits into three cases. There's the minimal general type case. These are, of course, projective. And here, again, you need to rescale omega t divided by t. And away from the augmented base locus of Kx, you converge smoothly to a negative Kähler-Einstein metric, again, which is the pullback of the ACDU against the Riahi, so-called singular Kähler-Einstein metric on the canonical model X-can. So here, this was again proved by Tian and Zhang. So the picture here is exactly the same as in all the previous lower dimensional discussions. So you have excellent convergence to an Einstein metric away from some natural bad set, which is the augmented base locus, or null, same as the null locus of Kx. And Kodara dimension 0 is even easier. Here it follows that Kx is torsion, so what I would call Calabi-Yau, and the metrics converge smoothly to Ricci flat. This was known for a long time. Finally, the really challenging case is the fiber case. So when the Kodara dimension is intermediate, so Kx is semi-ample, so you have the corresponding semi-ample Ithaka fibration, pi. The generic fibers are Calabi-Yau, smooth manifolds. And D, I will call the discriminant locus of Y, of the fibration, in a somehow not precisely proper sense, meaning D for me will include the singularities of Y, and then it will include the critical values of pi on the regular part of Y. So D doesn't have to be a divisor. It may have higher codimension irreducible components, but in any case, I'll call it discriminant nevertheless. And on the complement of the discriminant, the preimage of the fibers are smooth, Calabi-Yau, and there's again a Weil-Peterson form, semi-positive form, which measures the variation of the complex structure of the Calabi-Yau fibers. And Song and Tian constructed then, again, a twisted Kähler-Einstein metric on the base, minus the discriminant, solving the same equation as we had on the case of surfaces. And they prove a weak convergence of the rescaled flow to the pullback of this twisted Ke. So namely, the Calabi-Yau fibers shrink in infinite time now. So you still have this vibration picture, the Calabi-Yau fibers shrink at infinite time, and you're left with a limit which lives on the base. So this limit is the eta from the previous slides. So in this semi-ample case, the eta, I mean, the other two cases are stupid. I mean, maybe the first one is not, but in any case, in the interesting case, the eta is the pullback of this twisted Kähler-Einstein metric. So in particular, it is smooth on the Zariski open set. It has bounded potentials everywhere, so zero along numbers. And when you view it upstairs, where it's smooth, it has a kernel. The kernel, of course, are just the Calabi-Yau fibers. So they give you the Ithaka fibration. So you see, this expectation is precisely coming from what you have here. And there was a conjecture of Song-Tian that the convergence should be much better than weak convergence. It should be smooth, again, away from the singular fibers. So away from the preimage of the discriminant, you should have smooth convergence and locally bounded Ricci curvature. So it's known that you can't have locally bounded Riemann curvature in general. In fact, it's known that you have that if and only if the generic fiber is a torus or finally covered by a torus. So I proved this with Zhang. So if the generic fiber of the Ithaka fibration is finally covered by a torus, then you actually have locally bounded Riemann curvature, but otherwise you don't. And the best you can hope for is Ricci. So this was is basically an analysis problem. You need to prove a higher order derivative estimates for the solution of the flow. And there were many partial results by many people, or some of them by myself and collaborators. And finally, last year with Hein and Lee, we proved this conjecture in general. So this was a really long and hard analysis paper. So the upshot is that you have the best possible convergence away from the singular fibers. So the Calabi-Yau fibers shrink, but they do so smoothly. And also, if you restrict to a Calabi-Yau fiber and you don't rescale, so keep it of a fixed size, then you have, again, smooth convergence to a Calabi-Yau metric on each fiber, which means that under this collapsing, the fibers are becoming more and more Ricci flat. So it's asymptotically semi-Ricci flat, we will call it. And lastly, one can ask about the Gromov-Hausdorff limit of this flow. So again, rescaled, and the fibers are shrinking, so it should be something related to the base. So we now know that any subsequential Gromov-Hausdorff limit is homeomorphic to the base. This is a very recent work in progress, if you want, with Lee and Junshan Zhang. What we really would like to prove is that it's also isometric to the metric completion of this twisted Kähler-Einstein. So finally, it would be a canonical, this twisted canonical metric on the base and completed. So this is known in the log smooth case when the base of the Ithaka fibration is smooth and the discriminant locus is a simple normal crossing divisor. Then I did prove this with Yang Li a few years ago. But in general, this is still open. And we expect that some recent work of Gabor Sekihidi using so-called RCD spaces will be helpful to prove this one. So I'm almost done. I just have a final outlook slide. So I basically told you the whole story of the flow behavior and how we use MMP results to understand the flow. I didn't tell you anything about the proofs. They're all kind of analysis of in fact, the Monge-Ampère equations, which are what the flow becomes. But in any case, all the progress that I can see has been going in one direction, from the MMP or Kähler MMP to the Kähler-Ricci flow. And in particular, we can see that if abundance was proved, then we would have a basically complete now understanding of immortal solutions of the flow, because that was the only missing point to have the Ithaka fibration. On the other hand, even if you have all of MMP, still there's a lot of work to do to understand finite time singularities. So I think that volume non-collapsed ones could be approachable, but the volume collapsing finite time seems very hard, even if you have MMP. So that's a negative point. And the final challenge, of course, is to find something useful going backwards. So anything using the flow or its limiting behavior to help for the MMP. It's tempting to of course, this conjecture here is one mild attempt to try to help in that direction of producing some analytic object which may be related to abundance. There's also, one can try to speculate whether there's some monotone quantity along the flow. I think Zichuan was discussing this with me some time ago. For example, the Perron entropy, which is known to be monotone along the smooth flow. Can this be used to say something? And another point is that this picture that arises from this Cascini-La Nave and Song-Tian picture is very highly reminiscent of the Thurston and Perelman geometrization of three manifolds, but this should be taken with a huge grain of salt, right? So the limiting geometric pieces would be this Einstein or twisted Kähler-Einstein matrix, or in the Fano case, those solitons. So and the decomposition of the original manifold into pieces is simply the one given by MMP, so via birational or bimenomorphic contractions or those Fano fibrations. So again, there is a very vague analogy between the two. Can this be used to say anything? Can this canonical matrix in the limit be useful for something? So I will leave you with this, and thank you very much.
Thank you so much. Any questions for Valentino?
So maybe I can ask a question.
Yes.
So regarding the last direction from Kähler-Ricci flow to MMP or something like that. Very simple, very simple case. Very simple case. Suppose that you have a surface of general type with one -1 curve.
-2 or -1, actually. Sorry, non-minimal. Non-minimal, okay.
Non-minimal, yeah. So the Kähler-Ricci flow contracts the curve. Can you show that the limit is smooth without using Castanova theorem, just as a Gromov-Hausdorff limit or something like that?
That's a good point. You know, I actually don't remember if this is done. So one point is that the limiting metric, like when you hit this finite time, that limiting metric, I believe in general, is actually singular, like the metric itself. So it's not super useful to detect that the space underneath was smooth. You see however, maybe, yeah. So I don't know. It's a good point. It's a good question. Yeah. So all I can say is that even if you already know, which you do, that the contracted space is a manifold, this limiting metric in general will have singularities. And I think you expect to have a conical type behavior for those limiting metrics. They should form like a cone angle along the divisor. I mean, at the point where the divisor was. And perhaps from that and some other argument, one could try to argue that it's smooth, perhaps. But this seems hard, actually.
So maybe it could imply that the singularities are terminal and hence in the surface case smooth.
Yeah, okay, maybe this could be more plausible. Yes. Yeah. But however, I don't believe it's known, at least not to me, that they really are conical, like the metric singularity. But maybe on surfaces it's okay. Yeah, I'll think about it. I'll let you know if I find something.
I mean, of course, the same question could be for canonical. I mean, if you contract a -2 curve, you want to ask if it's
like orbifold. Yes.
Exactly.
Yeah.
So when you have how to say? So earlier you mentioned that when you have a final vibration, then the limiting the rescale limit converges to the Kähler-Ricci solid on the fibers. So how does the Kähler-Ricci flow restrict to the fibers as a flow?
It's not nice. Yes, it's a good point. So when you restrict the flow, it satisfies some equation fiber by fiber, which is not Ricci flow, because in general the fibers will not be totally geodesic with respect to GT. So yeah, this is actually a hard point. So unfortunately, the restricted flow is not Ricci flow fiber by fiber. Still, we expect this to be true. I think it's quite far. There were some recent results by Song-Tian and maybe Jian, but I don't think they are close to establishing this. Also, when I say converges weakly, I really mean modulo some diffeomorphisms, and even then the convergence will be only away from some high codimension singular set, and this diffeomorphism in the limit will make the complex structure will jump, right? So the final soliton does not live exactly on the same complex structure, but it could jump to a different one. So there are all these caveats which make this very far-fetched. Yes. So I think there was also a paper by Robert Bierman long time ago called something about relative Kähler-Ricci flow. where he introduced a variant of the flow, which was supposed to fiber by fiber do something like Ricci flow. And I unfortunately can't remember exactly what he proved. It was a long time ago. You could try to check. It's Berman relative Kähler-Ricci flow, something like that.
Okay.
Yeah.
And also, besides the immortal case, so when you have like a finite time singularity or like a collapsing to some not-word point, how much do we expect about the uniqueness of the converging metric?
Yeah, I think it's more or less clear that it will depend on the initial omega zero. Like if you change the initial omega zero, you will get different limits, even though it's in the same class. So if you change the class, everything changes. Right? You can see the limiting class in general different in finite time.
So I'm thinking like when it's like maybe the case when you have collapsing, but collapse to some, let's say, a minimal surface, like a canonical surface.
Yeah.
For
So
instance,
the issue is here,
or like a varieties of general type.
Yeah. So the metrics in this, when you run up, you have this, let's say, Fano vibration. You run the flow upstairs. You hit the singularity in finite time. So the say Fano fibers shrink. That metric that you get on the base is not canonical at all. Yes, it will depend on the initial metric. It will not satisfy Einstein equation. But the point is you should restart the flow on the base and then let it run, hopefully for a long time. And in the limit would be canonical, like this. Yes. So when you hit finite time singularity, nothing is canonical, and everything depends on the initial data. But if the flow has infinite time to run, then the limit is supposed to be canonical, like this. Yeah. That's another challenge of this finite time, that the limiting metric is not a priori determined somehow. Yeah.
Okay. Yeah. Thanks.
Yeah.
Could you say one more time what are the subtleties if you work with KLT singularities instead of smooth?
Oh, yeah. I didn't say it. You're right. Yes. Yeah. So there's actually 2 points about it. One point is when you add a boundary, right? So x comma delta. This is actually annoying. So let's say KLT. So the problem is that the natural type of metrics that one wants to use are so-called, let's say, conical metrics with conical singularity along delta. However, even the definition of what is a metric with conical singularity is only really done when delta is simple normal crossings support. So if the boundary divisors a simple normal crossing support, there is a by now well-developed theory of Kähler metrics with conical singularities. The cone angles are the coefficients of your delta, and then indeed you can run the Kähler-Ricci flow. You can say log version. Log Kähler-Ricci flow can be run, and everything works pretty much the same as long as you work away from delta, and then bad things happen. You don't precisely know the behavior in your delta. However, if at any point the boundary divisor changes and becomes not simple normal crossing, we actually don't have any theory about the geometric model to use. That's one really annoying point. On the other hand, if you have no boundary, then it's let's say KLT, but the boundary is 0. Still, one can run. There is a weak solution of the flow. So this was developed by, the theory was Bedford and Taylor, some weak solutions of Moore-Jumper equations. For the flow, it was done, I suppose, by Song and Tian. However, these weak solutions are very weak, and we really don't know the geometry, how they look like near the singularities. That's the main issue to prove anything interesting. These two points are extremely annoying. But other than that, formally the log story should work the same, and it does in a sufficiently weak sense, but not in a stronger sense. In particular, especially for those results where you have a fibration structure, let's say either Fano fibration or Calabi-Yau fibration, if the fibers have singularities, which of course they will in general, then we don't know how to do really much about those results that I explained. There's only very weak knowledge, unfortunately. So yeah, log Kähler geometry still needs to develop more.
Thanks.
Yes.
Other questions or comments for Valentino? Okay, if not, thanks again.
Thank you all for coming. Thanks.